And let us understand the next topic, which is magnetic. Right. Let us talk about magnetic fields and yes, we will talk about magnetic. Okay, so what is a magnetic force? For a charge, right? And this is also called Lorentz force. So we have an electric field, right? We have an electric field, and let's say we have an electric field. We have an electric field, and we place a charge in this electric field. So we already know that the electric force, this would be simply Q, right? Now, let's say the scenario is different, and we have a magnetic force. We have a magnetic field. We have a magnetic field, and some charge is moving. Right, some charge is moving with velocity v. So charge is moving with velocity v. Then what is the force? So then this is called the magnetic force, and this is defined as Q v cross v. This is what we call magnetic force. Right. And if we have both of them together, so electric and magnetic field, both of them together, then in that presence the charge is moving, then combinedly, this is called Lorentz force. What is that? This is the electric force plus the magnetic force. And this is so this is QV, and then this is QV cross V. Right, so Q we can take common, and this will be E plus V cross V. So this is the Lorentz force. Right. And there is a direct question on the basis of this one. So let us do that direct question first, and then we will move on to the trajectory that the charge particle takes in the presence of this magnetic field. So what is the trajectory, right? So we'll talk about that trajectory in a moment. And yeah, these things you guys already know. So let us do one question, right? Very simple question. And okay, product this thing. So what we need to have. Yeah, I guess in the this is so this is the question. and we have to use the idea of the cross. So we are given, right, we are given that the magnetic force is Q V cross B, and this is Q V cross B, and we have to find out that what is the magnetic field expression. We know that Q is 1 and V is 2I plus 4J plus 6K, and F is 4I minus 20J plus 12. So these are the values which are given, and we have to find out what is this magnetic field, right? So to calculate the magnetic field, what you will do? So let's say that magnetic field is this is simply Vx I hat plus Vy j hat plus Vz k hat. Right, this is the magnetic field. And we have to find out that what is V cross B. Q is 1. Q is 1, so we'll not, so this F would be 1 V cross B. So this would be simply V cross B, right? And we know that what would be V cross B. So if we write V cross B, so this would be Ij and K, and then V is how much? 2, 4, and 6, and V is Vx, Vy, Vz. And then we have to take that into account. So if we keep this thing, so I hat, and then we have this thing and this. So Vz, 4Vz minus 6Vy. This is I hat, and then what do we have? Plus, and this is written in minus. So minus j hat, and if we cover this thing, so this would be 2Vz minus 6Vx, right? And then we just add this thing, so k hat. So if we cover this thing, so this would be 2Vy minus 4Vx. So this would be the cross product, right? And if we write this thing down, so we cover this thing and then 2Vz and minus 6Vy, and then minus this thing is gone to Vy. Oh, so this one and then 2Vz and 6Vx, and then this is gone to Vy. So if we write force, force is given, which is 4I minus 20J plus 12K, and this is equal to 4Vz minus 6Vy I hat minus Vz and 6Vx, and then J hat, and then plus Vy minus 4Vx K hat. So if we compare these two things, right? So if we compare, so what would be 4Vz minus 6Vy? So this would be how much? 4. And if we compare this thing with this thing, so this is 2Vz minus 6Vx, and this is 20. And then in the last, we have Vy minus 4Vx, and this is 12. Right. So you see that this is Zy. This is one equation, this is second equation, this is third equation. So how do we solve this thing? Right? How do we solve this thing? So what we'll do is that first we'll solve second and third. So solving second and third. What we will do? So this would be, we want to cancel px, right? We want to cancel px. So 6 4 LCM is what? 6 4 LCM is 2, 3 are 2 are 1. So 12. So we will multiply this with 2. So this is 4bz and then minus of 12bx. This is 20. And then we have to multiply this with 3. So this is 6by and minus 12x. This is equal to 36. Now we subtract these two equations. So this is subtracted and this is 4bz minus 6by and this one is cancelled and this is minus 60. So what do we have? So this is our fourth equation, right? This is our fourth equation. We can take 2 common. So this is 2bz minus, or this is 4bz, so we can keep it at that way. So this is 4bz minus 6by, and this is 4bz minus 6by. Oh, these both are same, right? Yeah, so both are same, right? And this one, so these two equations are parallel, right? These two. Okay, so if we see these two equations, right, we cannot solve these two equations. These are parallel equations, so there would not be any solution. Did I make any mistake in this one? So B plus O, so this was B, B, and B naught. Okay, yeah, so B, B, and B naught, right? So if we write B, B, and B naught, so you see that Bx and By they are equal. In here they have given that Bx and By are equal. So Bx equals to By. This is given. Right. So we can write that in here. Okay. So this is yeah. Okay, so we got all these equations and no need to solve this one. And then this is given that Bx equals to By. So we can put all these things as B, and Bz is B naught. So let's put all these values. So if I write this thing as 2by minus 4bx equals to 12. So 2b minus 4b, that is 12. So how much this will be? So this is minus 2b. This is 12. So b is how much? Minus 6. Right. So this is the option that we are seeing. Is it clear, guys? Yes, is it clear? So this was given that B is B, B, and B naught, right? And we have to only use the property of cross product. So if it is clear, then quickly note this thing down, and then we will do the next problem. So we only use this third equation. Only use this third equation, and then we got our answer. So quickly note this thing down, and then we will do the next question. And if you guys have any doubt, you can ask. Yeah, whenever you guys have noted, please tell. So one thing is that without taking Bx, By, Bz in here, because I didn't see this part. So without taking Bx, By, Bz, we can always start with this thing also. So we can start with B and B and this was given, right? So you can start with this one and then compare and then you get this. But yeah, this is also correct. So from this one you will also get the result. But from this one you will get the answer quickly. I have written Bx, By, Bz separately. You guys can write B, B and because they have given it. Bx is B, By is B, Bz is B. Whenever you guys have noted it down, please tell. Yes, whenever you guys have noted. Okay, good. So now let us understand the next topic, which is uh, the magnetic force or the trajectory of a charged particle magnetic this is trajectory of a charged particle in the magnetic. So one case is that we have this magnetic field, right? I will write it in this way. We have magnetic field which is going right. This is the magnetic field, and this is showing that magnetic field is inside. So we already know that this representation is outwards. This representation is inwards. The magnetic field is inside, which is minus k hat dash, right? So this is now the charge particle is starting from the charge particle is starting from here and it is moving in this direction with velocity v, right? So then it will travel, and we know that this is the direction of the v vector, right? And the magnetic field is inside, right? So what would be the direction of v cross? What would be the direction of v cross v? So you see that v is phi hat direction, and then the magnetic field is minus k hat. So what is the direction of I cross minus k hat? So this would be minus of I cross k. And we know that I cross k is what? That is minus j. Minus minus will cancel and this would be g hat. So the magnetic force would be in this direction. This is magnetic. If the charged particle comes at this position, right? Let me draw this way. So if charged particle comes this position in here, so the magnetic force would be in this direction. If the charged particle comes in here, so this is the velocity. In here, this is the velocity. In here, this is the velocity. So the charged particle will follow a circular direction. Whenever you have the magnetic field which is perpendicular, so here theta is 90, right? So the angle between B and B is 90 degrees. And for this case, this would be in a circular motion. And in a circular motion, there is a centripetal force. Centripetal force is always in the direction of the center. So the F centripetal, this is provided by this magnetic force, and this is Fp. So how much is this thing? So Fc is mv squared by r, if the radius is r. And then what is this Fb? This is qb, right? So 1b will cancel, and the velocity that we will get would be r qb by v. And the radius of this circle that we will get is mv by q. So this is the radius of the circle, and this is the velocity of that particle, right? And we can also calculate the angular velocity, omega, and this is how much? So this is the angular distance, which is 2 pi, and the time period. And what is the time period? Right? What is the time period? Time period is whatever time it is taken to complete this one circle. So distance is 2 pi r, distance by velocity. Velocity is how much? So this is 2 pi r, and velocity is q b r divided by. So r will cancel, this m will go upstairs, and time period would be 2 pi m divided by q. So this is the time period of this thing, and then we can calculate the angular velocity as well, 2 pi by t. So that would be q by m, right? So all these things we can calculate, right? Please note this thing down, and if you guys have any doubt, please say. Quickly note this thing down. So this was when the charge particle is making 90 degree. If it is making 0 degree, if it is making 0 degree with the magnetic field, then magnetic force would be zero, right? So then there would be no circular motion. What if it is if it is making the, yeah, if it is making the 90 degree angle, then there would be circular path that it will follow. Quickly note this thing down, and yeah, and then we'll talk about what happens when it is making some arbitrary angle. So that thing will also. Whenever you guys have noted, please. Yes, whenever you guys have noted, please do. Just have to remember that this is so set repeated force would be equal to the magnetic force. If you remember this thing, then you can calculate what is velocity, what is radius, what is time period, what is angular, and how is. So if you can calculate time period, then you can calculate frequency. Frequency is f, which is 1 by t. So this would be qb by 2 pi. So all these things you can calculate. Yes, noted everyone. Whenever you guys have noted these steps, right? Then I will do the arbitrary angle scenario, and then we'll talk about the magnetic force between and magnetic force in the current carrying wire, and then I will talk about magnetic force between the parallel lines. Yes, guys, noted. Noted everyone. Are you guys there? Did you guys note it down? Yes, guys, are you there? Did you guys note it down? Okay, good. So now let us talk about the other topic. So when case two is when theta is arbitrary, right? Meaning that theta is not 90 degrees. So let's say we have this magnetic field, external magnetic field, and in this magnetic field you are throwing a charge in this direction. So this is charge and it is making an angle theta with the magnetic. So this is the velocity, right? So now this velocity will have two components, right? And we have already talked about the resolution of vectors. So this velocity will have two components. One would be one would be this one, which is v cos theta, and the other one, which is this one, and this is v sin theta, right? So now, due to this v sin theta, this is the magnetic field. So this v sin theta is the perpendicular component. This v cos theta, which is with the same angle as v, So this is the V parallel form. So V perpendicular will provide, this will provide the circular motion as we have seen earlier, and V parallel will provide the forward motion. So now the charge particle will follow this path, right? So this, oh, what happened? So this charge particle will follow, so this path, and this path is circular, and this is the forward motion. This is the forward motion, and this would be whatever this thing is. This is the circular motion, right? This one is the circular. So circular motion is happening due to v sine theta, and this is happening due to this. So this distance is what we call pitch, and this is a distance. So this would be equal to velocity into time, or speed into time. And we know that what is the speed in this direction? So that is v parallel into time, which is the one revolution time. That is the time, right? So pitch is given as, so pitch is parallel is v cos theta, and t was what? So time period was this qt by 2 pi or 2 pi m by q, right? So that we can pi m by q. So this would be the pitch, right? So this is what we call the helical path. So we have the circular path as well as the forward path. So this is the path that this charge particle with the arbitrary angle will form. So quickly note down this part, and then we'll do the next topic, which is the force in a current. Uh, Whenever you guys have noted, yeah. So whenever you guys have noted down this part, Okay, noted everyone. Good. So now let us talk about force in a conducting magnet. Force on conducting wire in the presence of magnetic. So obviously we are talking about magnetic. So we have some magnetic field, right? Let's say we have some magnetic field, and then we have this current carrying wire. So we have this wire which has a current, and this is moving this way. Current is flowing this way, and this is the magnetic field. So then this current carrying conductor will experience a magnetic force, and that would be equal to this would be equal to I L cross B, and L is the length of this wire, right? So whatever length we are taking, so that would be the force. And this is I L B sine theta. And for this case, we know that the angle between L and B is 90. Okay, so for this case, so this would be right. So this should be 0. So let's say the wire is in this way. In that case, if the theta is 90 degree, right? Okay, so this is 90 degree. So for this case, F would be simply ILB, and sine 90 is 1. Sine 90 is 1, so this would be FIL, and this is written as the PI. So this is the current this is the magnetic field, magnetic force experienced by the current carrying wire in this particular length. So this is the length we are talking about, right? And now, what would be the force? So what would be the force? Force in a parallel current carrying wire. What is the force between two parallel current carrying wires? Right. And let's say the distance between them is, let's say this is A, and let's say that, or we can write that this distance is R, right? And this is I1, and this is I2, right? And let's say that we pick a particular length. So this particular length is N, right? So we know that what is the force, or due to this I1, right? Due to this I1 current, there would be magnetic field at these points. There would be magnetic field at these points, and that would be in the inside direction, right? So magnetic field due to this wire would be inside. We have already discussed the magnetic field for a straight line wire. So this is the magnetic field which is inside. The current is flowing in this way. So magnetic force would be in this direction, right? So magnetic force would be due to this magnetic field, and that would be VI. And because the current is I2, so this is VI2 and S. This length is and can you guys tell me what is this magnetic field? Magnetic field due to I1. Can you guys tell me what is the magnetic field due to I1? This thing we already know. That magnetic field is inside and the current is I2. So for this particular length, this would be the magnetic field. Now I'm asking that what is the magnetic field due to this I1 wire? Yes, what is the magnetic field for a straight line wire? Okay, so this is mu naught and I by 2 pi r. This we have already discussed. So this would be mu naught and current is I1, so this is I1 and then divided by 2 pi r, I2 and L. So this is the force experienced by the parallel current wire and the force per unit length, F by L. So this is the force per unit length. This would be mu naught I1, I2 divided by 2 pi r. So note down these things and then we'll talk about moving coil galvanometer. So please note down these things, right? Please note down these 2 points. And then we'll talk about moving coil galvanometer. Yeah, quickly note down this thing and then we'll talk about moving coil galvanometer. Yes, note it, guys. Good. So now let us talk about moving coil galvanometer. Right? So in moving coil galvanometer, we have this system that we have this permanent magnet, and then we have the cylindrical coil, and this is wrapped up by this number of turns. So this is a soft iron core, and then this is wrapped up by the coils, right? And then there is this pointer, and then it is connected with this indicator or scale, and this is the deflection scale, right? And then the angles are marked in here. So if this thing rotates, this spring rotates. If this spring rotates, so there is a restoring torque in the opposite direction. So if you rotate this spring, this will be deflected and it will again want to restore its position. So there is a restoring torque or restoring of force or torque. And what is how much is that? That is equal to some K phi, right? Because we know that what is the restoring force? That is Kx. So similar to angular analogy, the restoring torque would be K phi. And before we talk about the torque in a magnetic field, so we'll have to talk about yeah. Before I talk about this torque, let us talk about that. What is the torque in a magnetic field? So torque in a magnetic field is simply M cross B. And what is this M? So this M is the magnetic dipole moment, and this is equal to how much? So this is equal to Ni. So this is the magnetic dipole moment. So this is Mp sine theta, and this is Ni, and this is B sine that, right? And this is what is called torque. Okay. And if the angle between them is 90 degrees, so this torque is simply NIA, right? So this is torque in a magnetic field. Now let us get back to this part that torque, restoring torque is K phi, and this is happening due to this magnetic field which is passing radially. So then we have 90-degree angle. So then this theta is 90 degrees, so this is NIA. And we know that this torque is how much? This is equal to K phi. So we can write this as NIA T, and then this is K phi. So we can calculate this deflection as NIA by T. So this is the deflection in the galvanic. Right. So this is the deflection in the galvanometer, and we can also calculate, right? So we can also calculate phi by I. So what would be phi by I? This would be simply NAB by K, and this is called current sensitivity. And if you multiply this thing with some resistance R, right? So we know that phi is NIA by K. If we multiply the resistance of the galvanometer, so IR would be V. So this is NBA divided by KR. And now we take this V the other side. So phi by V, this is N, and AB by KR. So this is what we call the voltage sensitivity. Right. So this is voltage sensitivity, this is the current sensitivity. And this is working on the principle of this restoring torque. So yeah, this is all about the moving coil galvanometer. Please note this thing down, and then yeah, this chapter. So quickly note this thing down. Note this thing down, and then we'll talk about next chapter. Whenever you guys have looked at what disconnected. So I really got disconnected. Now, then Ali, you have to tell me whether you have noted or not. Yeah, whenever you have noted, Ali, please tell me.
Enter.
Yeah. Okay, so this topic is completed, and one more thing is remaining, right? So one more thing is remaining is that how we can make an ammeter, right? How we can make an ammeter using the galvanometers. Conversion of galvanometer into ammeter. And how we do that? So we add in the galvanometer, let's say this is the galvanometer, which has the resistance G, and the current is passing through it is Ig. And we connect a shunt resistance, right? We current a shunt resistance which is S to it, and then this device becomes, right? So this device becomes this whole device becomes the ammeter. So this is what we call the ammeter. In ammeter, you have a galvanometer, and parallel to this galvanometer, a shunt resistance is connected. So then you can calculate what is this shunt resistance, right? So you know that from junction root, let's say I current is passing. So this is Ig. So this would be I minus Ig, right? So this is the current, and we know that these are two are parallel. So voltage in galvanometer, that would be equal to voltage in the shunt. So what is the voltage in galvanometer? That is Ig Rg, right? Let me write it as I G. So the voltage would be equal, and this would be equal to voltage in shunt. So what is that? That is current into this shunt resistance. So shunt resistance is how much? That is equal to Ig divided by I minus Ig, and then it is multiplied with this resistance of the shunt, resistance of this galvanometer. So this is what we call shunt resistance. Right. Similarly, we can make okay, Nabil, you have it right. So similarly, we can make a voltmeter, right? So conversion of voltmeter by conversion of a voltmeter, or let me write it as conversion of galvanometer into a voltmeter. So this becomes ammeter, and this becomes voltmeter. And how does it become a voltmeter? So what we will do is that you have this galvanometer, right? You have this galvanometer which has this resistance, and then you connect a load resistance or a high resistance R in series with this, right? and then you calculate, let's say I current is passing, say I current IG is passing through it, and then you connect up parallelly. So then you connect whatever what you want to measure. So that thing you connect parallel, right? So let's say you want the voltage of this device. So this thing is what we call, this is what we call the load. And you connect a device parallel to it. So that device, so for the voltage of this device, we can measure, right? That, yeah, let's say the I current is passing. Voltage would be equal to I and Rg plus R. So we can calculate this R. That would be how much? So this is V by I, and then this is Rg plus R. So we can calculate this R using V by I. So this is the load resistance of this calculator. So that is how we calculate all these things. And yeah, so this is done. So this chapter is done. Please note down these two portions and then we'll start here. Next chapter is done. Quickly note down this. So you guys already know that the ammeter is connected in series to measure the current. Voltmeter is connected parallel. So this voltmeter, whatever this voltmeter is, so you connect the voltmeter parallel to whatever the device you are measuring. This device voltage you were measuring, so you connect this thing parallel. Right? So that is yeah. Whenever you guys have noted these things. So whenever you guys have yes, whenever you guys have noted. Okay, okay. Now let us uh, now let us move on to the next chapter, which is EMI. And what have we learned in that EMI? So what you guys have studied? First thing that you guys have studied is magnetic flux. That, what are the things that you guys have studied in, right? And in EMI, what are the things? particular study. EMI meaning electromagnetic induction. So induction meaning that we are inducing the electric current, and we are inducing the electric current by means of changing the magnetic flux. This is what we are doing, right? We are inducing the current, we are generating the EMF by virtue of magnetic change in magnetic flux. That is why this is called EMF, right? To understand this thing, first we have to understand what is magnetic flux and what is magnetic flux. So electric flux, you guys already know, right? Electric flux, you guys already know. And this was what? So this was phi E, and this was E dot A, right? This was the electric flux, or simply E dot S, whatever you can write, right? So A and S are equal. So the number of electric field lines passing normally to the area surface area. So that is what we call electric flux. So magnetic flux is same, right? What is magnetic flux? So magnetic flux is the magnetic field line passing normally to. So we have this magnetic field line, right? This is the magnetic field line, and this is some coil from which this the magnetic field lines are passing. So this would be the number of magnetic field line, which is 1, 2, 3, 4. These are passing normally. So phi B would be right. This is what we call magnetic flux. And let's say that if the area vector is this one, so this is how the area vector is there, and it is making this thing is making the angle this. So let's say this is making an angle, right? Let's say this is rule. So this thing is making an angle theta, right? Then what is the angle that we have to take? So the normal vector would be this thing, right? This would be the normal vector, right? And then the magnetic, let's say the magnetic field is passing through this area as this one. So this is not the theta that we should take. So the theta that we would be taking is with this normal vector. This is the normal vector of the surface area, right? So then this would be the angle which is 90 minus theta. So this would be the angle that we, and magnetic flux would be how much? So this would be BA cos theta, right? So this is what we call magnetic flux, and it is denoted by Weber, right? So this is denoted in Webers, and this is the unit of magnetic flux, right? And it can be also represented as magnetic field is Tesla, and this is the area. So this is also written as T and meter square, right? So we can also represent it as Tesla meter square or Weber. Simple notation is Weber, right? So this is magnetic flux, and why this is important in EMI. So this magnetic flux is related with the Faraday's. This is related with the Faraday's law, and Faraday's law states that we can generate the EMF. EMF we can be generated by changing this magnetic flux, right? So this is a very important law, This is a very important law, and it says that EMF can be generated by changing the magnetic flux, right? And this flux is dependent upon B, A, and cos theta. This flux is dependent upon magnetic field. This is dependent upon area. This is dependent upon theta. So we can change the magnetic flux. We can change the magnetic flux in three ways, right? One is that we can change B, keeping A and theta constant, right? Or we can change, so we can change B only, or we can change area, or we can change theta. So where have you seen this thing? Where you have you seen this thing? Do you guys recall? Where do you see this scenario? Where do you see this scenario? You guys remember where do you see this scenario? Yes, guys. You guys remember where do you see this scenario? This is in the example of AC. This is in the example of AC generator. In AC generator, you only change the angle between the coil, angle between the aperture and the magnet. So you just change the angle. And then by changing the angle, you can generate the that is this minus sign represents the length of right. So this minus sign is represented by this. And yeah, so this is what we call Faraday's law and magnetic flux. And then we will talk about the mutual inductance and self-inductance in the next class. And then this EMI chapter would be over, and then we will talk about AC chapter, right? So that will talk. Okay, just quickly note down these, right? Just note down these, and right, and then we can then we'll stop, and in the next class we'll have some questions depending upon the semantic flux, Faraday's law, and all some questions, right? How we can generate, how we can use this Faraday. Note down this thing, and then we'll stop. Guys have what to say. Okay, nothing got
Done, sir.
done. Okay, so we'll stop here and see you guys tomorrow, and we'll do some questions, right? So bye bye, Arya. Allah Hafiz. See you tomorrow.